Welcome to another class on the periodic table. Your favorite tutor, Yomi Omorewa. And I'd earlier explained this topic and I'd given five properties or six properties of the periodic table. And I said then in that video that there are factors that affect ionization energy, right? And I did mention about five of them. But I'm going to see if I can explain like four today, or if I can explain four, okay? If time will permit. I have number one, the atomic radius, the nuclear charge. Number three, we have the screening or shielding effect. We have the stability rule and the type of orbiter. These are various factors that affect ionization energy. Factors affecting ionization energy. Factors affecting number one, atomic radius. Number two, nuclear charge. Number three, screening or shielding effects. Number four, stability rule. Number five, type of orbiter. So we have these five factors affecting the ionization energy. And I did explain what ionization energy is in the last video, and I did say that ionization energy increases across the period because of the increase in nuclear charge, but decreases down the road because of increase in atomic radius. Can we express that mathematically? So we can say that ionization energy, okay, is directly proportional to nuclear charge, but inversely proportional to atomic radius. Yes, we can conclude this. Now, I'd like to explain again what atomic radius is. Atomic radius, we say that is the size of the atom, okay? Which is the arc distance between the atom that is inside the nucleus and this place. So the arc distance between these is what we call the size of the atom, the atomic size, okay? And the atomic size tends to increase when the number of share increases. I think that's a common sense actually, because if I increase this now what do you expect? It's going to increase obviously. This is longer than this. So the more the share increases, what happens? The more the atomic radius also increases. So the more the number of shells, the more the atomic radius. And when that happened, that tends to now counter the nuclear charge, because the increase in atomic radius will affect that of the nuclear charge. This is why we said here that ionization energy will increase when nuclear charge increases, but it will decrease when this increases, or it will increase when this one decreases. Okay, so they are inversely proportional. So this is proportional, directly proportional, while this is inversely proportional. Now come to nuclear charge. The nuclear charge, I did say that as the number of protons increases, because the nuclear charge refers to this thing. Look at the nucleus. This is the nucleus. So inside the nucleus, there are two things here, the proton and the neutron. And we said that the nucleus is positively charged, right? Why is it positively charged? Because there's a proton inside, and that proton is carrying positive sign. And so, because there's a proton inside, If you have sodium, for example, 281, and you have another like magnesium 282, and you have aluminum 283, you will observe that they have the same number of shell. The shell does not increase, but then the proton number increases. That is this number. So this is what happened when you have a nucleus here, and then remember there are electrons outside here. Okay, so there's an attraction. We call it electrostatic attraction between the nucleus here and the outermost shell. Okay, so now, so when the number of proton is increasing, sorry, this is 3. When the number of proton is increasing, the implication is that it increases the positivity, it increases the proton in the nucleus. Yes, it increases the proton in the nucleus. And when the proton in the nucleus increased, then the nuclear charge automatically is affected, which are invariably or directly influenced the ionization energy to increase. Because ionization energy says that is the minimum energy required to remove an electron. What does that mean? Removing electron from sodium is easier compared to magnesium. Of course, sodium just has one. It's very easy. It's easier to remove 2 from magnesium compared to what? To aluminium. It's easier to remove 3 from aluminium to silicon 284. Do you get now? So the more the number of proton increases in the outermost shell, what happened? The difficult it becomes to remove the electron from the outermost shell. Okay, so that's what this implies, and I'm sure the explanation is quite clear to you. Now, screening or shielding effect. Many students don't understand it, and Tutor Yomi is here to demystify, to break down these concepts so that you can get it. If you're in 100 level or 200 level and you're learning this in school and you have not gotten it yet, what do we mean by screening or shielding effect? Let me use sodium for example. So let's look at sodium. Let's look at sodium. Sodium has 281. That is, this first share is 2. So 2, 2, 2, and 2. And then the last one is having just 1. Please listen very well, students, and pay attention to this screening effect. If you look at this, when a child, this is a child in the outside, and this child is walking while rain is falling from up, and the child now has an umbrella on its head. So the umbrella is now shielding. You know, rain is coming now, right? So the rain is not able to get to the child's head. Why? Because there's something that shields that rain from getting to that child. Why? What is that thing? The umbrella. So the boy or the child is not wet because there's something shielding that child from the rain, and that's the umbrella. The same thing applies to screening or shielding effect. What happened here is this. Now, if you look at this, how many electrons do we have here? 2 electrons. Please take note. Let me quickly say this. This is sodium atom. Sodium atom means that the number of protons and electrons are equal. That is why atoms are neutral. They are neutral because the number of protons equals to the number of electrons. So it means that it has, if I say 2 protons and I say 2 electrons, don't be confused. So there are 2 electrons here, but here there are 8 electrons, right? So these 2 electrons and the 8th electron are called the core electron. What did I call them? Core. The cocoa, the real one, the core electron. Why this one that is outside here is called the valence electron? Oh my goodness. Do you understand me at all? Do you get it? I said this one and this 8 here. What is it called? Say it again. Core electron. And the last one here, which is just one, is what? Is valence electron. Now, what is happening here? This particular valence electron is being shielded, is being screened, is being shielded, is being protected by who? By the core, by the two core, by this core electron and this core electron. So what then is the screening effect? The screening effect is the repulsive force that is being exerted, listen to this, by the core electron on the valence electron. The repulsive force, what does that mean? Because between this nucleus and the electron is electrostatic force, electrostatic attraction. But around the electrons themselves is is repulsive force that will take place. That is, they will repel, repelling force, repulsive, repelling, and all that. Okay? So that particular repulsive force that is being exerted now by the core electron. What are the core electron now? Look at them here. And then on this valence electron is what we call the screening or the shielding effect. Does it affect ionization energy? Of course it does. Let me show you quickly. Let me show you quickly. If you have 2-3 people here using this one umbrella, obviously, now let me not even use that illustration. Let me say it again. This is magnesium. This is sodium. Let's turn it to magnesium. Let's turn it to magnesium. If we turn it to magnesium, it will be 2A2. So we have another one here. If we turn it to aluminium, it will be maybe something 3 here outside. Do you observe something here? The more the electron that you have in the outermost shell, the more now that you have, the more the screening or the shielding effects. I repeat. The more, that is, if you have this now, look at this. Because somebody may ask, hold on, let me turn it the other way around. So I just said something now that might not be totally correct. Somebody may ask, okay, does screening or shielding effect increases across the period? Does it increase down the group? Hey, question, big question. Screening or shielding effect increases down the group. Excuse me, why? Because of the shell. So the explanation I gave, this last explanation, so I want to counter it now. If you have lithium and lithium has 2, you have sodium has 3, you have potassium has 4. It means that the more the number of shells, the more there is a protection on the outer valence electron. Yes. So, and the more the protection on the outer valence electron, the more the screening or shielding effect. Very simple. Very simple. But across the period, what happened to screening effect? You can either say it is constant or maybe it's decreasing. Because the effect is not felt. Why? Because the shells are the same. The shells are the same. But down the group, it is increasing. And that affects the nuclear charge. There's another word called effective nuclear charge. Effective nuclear charge, which is equals to Z minus X. You may need to write that down. Where Z is your atomic number and your X is your screening or shielding effects. Okay? And whatever you get, it can be calculated, but that's not what we are doing. It can be calculated. Your atomic number and your screening effect minus whatever you have becomes your effective. But this is the formula. This is the relationship. So that's how screening effect also is a factor affecting ionization energy. And then we have the stability rule. The stability rule, there's a rule called stability rule. What does the rule state? The rule states that fully filled orbiter or half-filled orbiter are more stable than others. fully filled orbital or half-filled orbital are more stable than other. What does that mean? If you watch in period 3 in the periodic table, period 3 is sodium, magnesium, aluminum, silicon, phosphorus, and so on. In this period 3, we are told that ionization energy increases across the period as you move from left to right. Is that so? Yes, that's correct. But then, we realize that that statement is not absolute. It's not totally correct. It is true that the ionization energy increases until you get to phosphorus, for example, and sulfur. And let's write the electronic configuration out. 1x2, 2x2, 2p3, 2p6, 3x2, and 3p3. That is for phosphorus. Sulfur now. 2x2, 1x2, 2x2, 2p6, 3x2, and 3p4. This is for sulfur. And we have been taught or told that ionization energy increases across a period. But as soon as we'll get to this place, we realize that the maximum electron for p orbital, the maximum electron that p orbital can occupy is 6, right? X is 2, P is 6, G is 10, and F is 14. Okay, so know that. And but what is the half of 6? We have 3. And the rule, stability rule, states that fully filled, either you are fully filled or you are half filled, they are more stable than other type. So this one is neither fully filled, neither is it half filled. It's even more than half. So, and it's not fully filled. Obviously, phosphorus is more stable than sulfur. And the fact that it's more stable than it, then its ionization energy is higher than sulfur. Now, so it therefore means that stability rule 2 interfere with ionization energy, thereby becoming a factor that influences ionization energy. In case what I've explained so far is still looking ambiguous to you, difficult for you to comprehend, drop your concern in the comment section. I'll be willing to answer you. But these things are very, very simple. I'll be waiting for your question in the comment section. You can try the last one, type of orbital, and let me see how that affects ionization energy. Till I come your way again, I remain my humble self, Yomi Omora. Bye.